This is finally the quantum mechanics lecture. We've been alluding to quantum mechanics all semester to tie everything together. In a weird way, quantum mechanics does tie everything together because it's the most fundamental theory we have right now in terms of explaining the reality that we experience. It describes things on the lowest level. So when we think about reductionism in science, when you take the complex and you break it down into simpler and simpler and simpler levels so that you can then understand things at the most basic level and then rebuild your understanding from there, quantum mechanics is the most basic level. The problem with quantum mechanics being the most basic level is it doesn't seem to make sense compared to our everyday experience. Rather than being a simple explanation that then gets built back up into what we see every day, it surprises us. Now it's real and it's true what I'm going to tell you today because we can utilize these tricks, so to speak, in reality to accomplish some pretty interesting and amazing things. But on the most fundamental level of reality, reality sort of falls apart. It becomes probability. Everything is the probability of something happening. And when we measure that probability, we can then start to rebuild it into an expectation of reality that we actually experience. Now, the story behind this is actually very interesting, I think, because it brings us full circle with the other lines of reasoning that we've been looking at. If we think about it historically, from Galileo and Newton forward, we've got the laws of motion that describe everyday objects up to planets and things like that, but was limited in its overall scope in explaining all motion that we see in the universe. Einstein's relativity partly explains all of that, but it was also partly to try to explain light. Our discoveries about light and electricity and magnetism along the way were also feeding into this overall sort of picture of our universe and our reality that needed deeper understanding. Particles like the electron and the photon were discovered, and with the measurement of the photon itself, the amount of energy in a photon, Max Planck gave us the Planck constant, the smallest thing that can exist in the universe, but also an image or an understanding of light as particles. Sort of settled the debate finally about whether light is a particle or a wave. It's both. Now, that was, in a nutshell, the most startling recognition. I mean, it's something that physicists had to finally accept. For centuries, they'd been debating, is light a particle or is it a wave? It's one or the other, because everything in our everyday experience is one or the other. Things are either particulate, made up of smaller things, or it's energy traveling through a medium of some sort, like sound. Sound is not a particle. It's vibrations of energy that travel through the particles of air between my throat and your ears, right? You can set up a wave in water, and you can watch the energy move through the water. The water just moves up and down. The water's not moving with the wave, it's just being moved by the wave. The wave is energy, and we've always thought of things that way, either particle or wave. But with the recognition of light being both, we had to completely change the way we look at things. And this was a real challenge. I'm going to show you the experiment that sort of demonstrates this particle-wave duality first, and then we'll talk a little bit about the challenges that early quantum physicists faced accepting this. And I'll tell you right up front, Einstein had a really hard time accepting quantum mechanics. He fought against it most of his career. Said, no, that's not possible. You have to prove it to me through experiment. The quantum physicists did, and Einstein had to accept the results. And so over a long period of time, he helped push the development of the ideas to where we have them today by being that healthy skeptic that we talked about at the beginning. One of Einstein's greatest gifts to us was being that healthy skeptic that pushed quantum mechanics to where it is today. So we'll look at this historically in a little bit, but first I want to show you this YouTube video that sort of talks about the particle wave duality of light. I started off like this because I wanted to sort of present you with a couple challenges about how could this possibly be true, and then we'll address that. Now, this particular YouTube video does come from a more dubious source than I typically will select my videos from. Taken out as a snippet, it's fine. But I don't recommend watching the movie it comes from with any expectation of them of reality. It's from what was the name of this thing? Down the Rabbit Hole or something like that. It was a documentary that was trying to take a couple misconceptions about quantum mechanics and build it into a sort of mystical thing. Anyway, but this video is actually the best rendering of this experiment that I've seen.
And here we are, the granddaddy of all quantum weirdness, the infamous double-slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange netherworld of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
All right. So again, don't watch the documentary What the Bleep Do We Know. You saw the little poster for that on the, or if you do, watch it and sort of chuckle because it really is not a very good documentary. It takes what just happened and then extrapolates into an area that, again, is a bit of a misconception. So let's go back, though, to the challenges that particular video does present to us. The measurement problem is what this really points out, and that is that you can't look at the electron and determine where it is and measure its properties at the same time. Now, this is a bit odd. This is really something we're not used to. We're used to being able to sort of sit in the background and watch something without getting directly involved with it, right? Think about Jane Goodall in the jungles watching the chimpanzees. At least initially, she was hidden. She didn't allow herself to be seen. She watched their behavior as an unattached observer. That's ideally what scientists want to be able to do. But we can't do that at the quantum level. We have to interact with quantum particles in order to make a measurement. Now, I'll ask you in that video, again, they were alluding to, again, the misconception that the recognition of the measurement is what set its attributes. I'm going to use terms like attributes to say, for instance, the electron has a particular spin. It can go positive or negative. It has a particular momentum, depending on how fast it's moving, those kinds of things. So those attributes are in superposition until you measure them. An electron can actually take on many different possible attributes depending on the measurement. If the measurement is in our minds, then we create reality, and that's where the movie was trying to go. And I'll try to build on where that is undone in a little bit too. But let's get to the real fundamental problem, and that is, since we are limited by the measurement of something in order to know where it is and what its properties are, what does that say about reality? Are we at our limit in terms of our observing reality, and really it's happening in ways that we can't observe? Or, as Werner Heisenberg suggested, is that just the way it is? Reality really is probability. That's the best we can do. Not only the best we can do, but that's the way it really is. Everything is in superposition and can be described as a wave of possibilities. We'll get to this wave function in a minute. And then when a measurement is made, that sets things in one particular way. Now, in the experiment, what do you have to do to measure an electron? What do you have to do to peek at the electron? What does that little eye camera represent? It was, essentially, yeah. They were using a photon of light to say, okay, here's the electron, but the photon, of course, changes the electron. That's the measurement. As soon as the photon strikes the electron is determined to be a certain place. In the dark, the electron it exists in all of its possibilities. It's in superposition. We have to use something to make a measurement, right? Light is our most fundamental measuring instrument. It's again, another quantum particle. We can take a single photon and strike a single electron. This is actually how solar panels work. Einstein won his Nobel Prize for this discovery more than his theories of relativity, and that was that a single photon can cause an electron the charge to move from electron to electron. So you can use sunlight to generate an electric current. It's called the photoelectric effect. And this one-to-one relationship between photons and electrons really goes more fundamentally than even that, because in every atom, and I've said this numerous times, the photon, which carries the electromagnetic force, is actually what's holding that electron in its orbit. It's keeping it in that atom. In other words, it's keeping it real. It's making it part of a real atom. Without that interaction, the electron is in more than one place at a time. It's everywhere within the possible, within its probability range. So this was a big challenge, though. And so there's an interesting thought experiment that Erwin Schrödinger proposed to try to challenge the idea that Heisenberg put forward. It's called Heisenberg's uncertainty principle, meaning we really cannot know where an electron is at any given time and also know what its spin and momentum are. We can identify, we can hit it with an electron and say, okay, there it is, but at that point we don't know what its properties are. We can't measure its properties. If we let it fly around in its orbital, then we can measure its properties, but we can't say where it is. It's everywhere in that range at the same time. And so that's what's called the measurement problem. All right, make sure you know, Heisenberg, Werner Heisenberg, not the actor or the character. Okay. That is where that name comes from, though, which is what made that kind of funny for for people who were aware of where he got the name Heisenberg from. Being a chemist, quantum chemistry is really the level that chemistry is done today. We can control chemical reactions at the quantum level, so it's an interesting. Okay, let's see, go this way. Let's look at Schrödinger's challenge. I call it Schrödinger's box or Schrödinger's cat. I want to expand this picture real quickly, and then we'll go back. But here's the idea. Schrödinger was basically saying, well, you know, I don't think that reality can really exist as probabilities. I mean, yeah, he wrote the equations that describe it, but he said there has to really be something already, determined. It's just our inability to measure it. And here's why he said that. What if you put a cat in a box? Okay, you can't see the cat because it's inside this box. Attached to the box is a little switch that can break open a vial of toxic gas that would kill the cat. The problem is that the switch is going to be triggered by the release of a radioactive particle, which is completely random. So we cannot say ever when that one particle is going to be emitted or not, which means we don't know whether the cat is alive or dead until we open the box. Make sense? If this is a quantum cat, it has to be both alive and dead at the same time. It's in superposition until we measure it. So as he was saying, is a cat can't be alive and dead at the same time. So the suggestion being, well, then a quantum particle can't be both different things at one time. But in fact, this is a little bit of a misdirection because we're talking about such a large object. You and I are made up of quantum particles, but they've already interacted. So they've already been determined. They've already been set. If we were to, like Lucy, just undo ourselves and become completely quantum again, well, then they could become whatever else they might want. Could possibly be, which is how she supposedly can be anything that her mind sort of sets herself to be. She has control of her wave function that can determine the states of each of her quantum particles. But Schrödinger's cat has become sort of a famous experiment because it's a way of posing that challenge that Schrödinger proposed. Now again, he eventually wrote the mathematics that describe the probability functions of quantum particles. They're called the wave function. And every quantum particle has a wave function. And there it is. I'm not going to try to explain that. But the graph, at least, does kind of show how a quantum particle could be one place or another, or in one state or another at any given time. It's in superposition. And that's just the way it is. Now, again, I'm not going to spend as much time trying to develop that idea into modern chemistry or physics, more than I want to try to play around with some of the ramifications that this presents us with, some of the challenging ideas that are out there and are misunderstood quite often in documentaries like What the Bleep Do We Know? And that is that, what does this tell us about reality? The famous quote was, "Is the moon really there if nobody is looking?" In other words, all the quantum particles of the moon are in superposition. They can take any state whatsoever until they're measured. Where does this measurement happen? Is it when the sun shines on the moon, or is it when somebody looks at the moon? Because mathematically it could be in either place. So again, like Schrodinger's cat, just that question posed the issue of how do we describe reality? And of course it's when the sun shines on the moon, right? It's all the photons and neutrinos and everything streaming forth from the sun, striking the moon and so forth. If there were total darkness and there were no interactions with photons or anything else, then yes, the moon, all the particles could be in superposition. We can put particles in superposition. We can separate them from their interactions. We can unentangle them and put them in a quantum state and use those particles in quantum computers and in other ways. As a matter of fact, that's one of the most promising applications of quantum technology, could be a quantum computer. If you think about a normal computer, and I'll come back to this a little bit, but a normal computer works with little switches that essentially can give you a series of ones and zeros. That's a digital language, but it's two possible states. So every calculation is basically done in a series of this binary code. A quantum particle, on the other hand, in its quantum state, can be more than one thing at a time. It isn't just 1 or 0, it's 1, 2, 3, or 4, or I just describe it that way. It could be 4 different states, or 16 different states, depending on the quantum the particle we're talking about. So you could potentially do, instead of 1 calculation at one time, 4 or even 16 calculations at one time. And if you could do 16 calculations at one time within one computer, you would have an exponentially more powerful computer than what we have today. Now there's some challenges. Again, they're working on this. There are some simple quantum computers that can do some simple calculations, but to get it to the point where it could really become the supercomputer that it promises to be, we have to overcome a few other issues, and I'll talk a little bit about how this might be done later too. But I wanted to bring up Niels Bohr before I go much further, because he brought about this question of reality. How do we actually then interpret reality? And basically he suggested that rather than try to fix the equation, so to speak, we have to assume that every possibility does exist. Every possibility does exist in superposition, and therefore plays out in our reality in one specific way, because that's what we experience. But in other, what it led to is other worlds, other universes, it would play out in the opposite ways. It would play out in a different way. Now we're going to see I'm going to look at the multiple universe interpretation, what we call many worlds, in terms of quantum mechanics in a minute, that this particular challenge led to, because it suggests that. Now he didn't exactly claim that. He was just saying it just so happens that what we actually see is one possible series of events based on this quantum reality. There's going to be another interpretation of multiple universes in string theory, which we'll get to next time, which is actually a lot more realistic than the one we're going to see here in a minute. But it does pose this interesting question. Before I do that, though, I do want to describe just what we mean by quantum mechanics, because I want to develop what quantum technology is and where it's going and why it's so exciting, because this week's lab has to do with the physics of the impossible, which has a lot to do with this technology and where it might take us. If you look at this diagram here, this explains quantum mechanics. These are, if you recall from the periodic table, the orbitals in which different electrons can occupy. The 1s and 2s, those are the innermost orbitals, those 2 electrons. The p orbitals can then occupy a different level, and the d orbitals a 3rd level. Now, you see 4 levels here, and what this is showing you is that electrons can actually move from one energy state to another. You hit it with a photon, it can jump up from one level to the next. If it emits a photon and releases that energy, it can drop from one level to the next. The point is, it can only be at very discrete points. Those very discrete levels, it's either here or it's there. It's never in between. Now, again, I don't know how much that just makes you shake your head, because I can't just be either here or in that chair, right? For me to get to that chair, I have to travel from here to there, right? That's what's normal. You can't just be here at the end of it'd be nice if you could just snap your fingers and you'd be home. But you can't do that. You have to get in a car, you have to drive. I mean, there's a certain amount of time it takes to cover that distance. This is what Einstein's relativity says. Nothing can just go from here to there without traveling in between, without some time elapsing. But an electron can. It can simply go from here to there without going in between. That's really startling. And in our everyday lives, is this really startling? Probably not. But in the applications, it is. Because this is how a transistor works. And you know the term transistor because from transistor radios to today, this is what makes this work, the computers. It's what makes your cell phones work. These transistors in your devices take advantage of these quantum states, these discrete points where electrons can be. And being able to switch from one to another and back and forth is how we generate that binary code and everything else about it. If it could be in between, it wouldn't work. It couldn't be 1 or 0. It would have to be 1 to 0. Well, you can't do a calculation on that. Okay, so it really is amazing that that's how things work. Let me go back to this a little bit. And look at some of the other strange things that quantum particles can do. That's the most fundamentally important one, and this again is sort of what the quantum physicists really were able to determine by experiment and describe very early on. This is the basis of quantum mechanics. Linus Pauling again won a Nobel Prize for this, for figuring out that electrons are paired in these levels and that they exist in these discrete levels. It's what Bohr and all these other quantum physicists really figured out. But they can not only go from one point to another within the orbital, but they could jump from let's say one atom or one place to another across a barrier. Even if there's something in between that would normally block the electron, they can just jump over it or through it or somehow. It's called tunneling. They can go through a barrier without having to actually, again, it just goes from here to the other side somehow. Yeah, you had a question.
So you're saying, Dr. Hope, that it's not moving at all, it's
Right.
not traveling.
Right.
Is that because you can't measure it, that it's moving so fast that it can't be measured,
No.
that you would just say that it's here and now it's there?
No, because we could measure it with light, right? If it is traveling, it's faster than light, which, again, relativity tells us can't happen.
It can't measure.
Right. Well, there could, now again, whether or not it's traveling at a speed that we can't measure because it's faster than light is sort of irrelevant because everything else we know is controlled by the speed of light, so the quantum particle is outside of that law. Again, Einstein really argued against this, so that's not possible. It's not possible that the electron can do that. Light is the speed limit of the universe. Nothing can travel faster than that. It can't just go from one place to another, and it can't travel faster than light. Experiments proved him wrong. Experimentally, we can show that this is true. Matter of fact, if tunneling didn't happen, your cell phone wouldn't work. Okay, and the equations, the wave functions, can calculate the probability that an electron goes from one place to another. Now, if you have just one electron, you can't, again, like the radioactive particle, you can't predict one electron. That's impossible. But if you have, 10 to the 1,000 electrons, which you do have in almost any given wire or even a small amount of metal, then you can calculate the probability of electrons that will do that. And very accurately say, of this many will do this in this given amount of time. It's the same thing with the half-life and how we use radioactive isotopes to date time. Any single particle behaves randomly, but together over time, the probabilities become set. And we can calculate those and we can use those as tools. Same thing with these quantum particles. They really do just go from one place to another. Now, if they're traveling just faster than light, okay, that's sort of an irrelevant way. That's like semantics, because we rely on light for all of our understanding of reality. So it's essentially, faster. And this is also why, if we were to travel faster than light, we would have the same we would be under the same kinds of questions. That's why, can we travel faster than light becomes a really interesting question. And the solutions are in wormholes and relativity rather than the quantum mechanic level. This level, though, this is how a teleporter might work. If you could disaggregate all of your wave function and then send that wave function somewhere else, you could potentially send all that information and reconstruct it somewhere else. Now, the issue with quantum teleportation, which is something that has been done with an atom, just one atom, but basically it's taking the information, sending the information somewhere, and then reconstructing that into an exact copy of the original. So if we had a quantum teleporter and you stepped into it to take a trip to Mars, you'd be two of you. You'd be in two places at once. Now, once there's two of you, you're separate things and you start behaving in different ways. But at that point where you teleport yourself, you send an exact copy of yourself. If we could get to the point where we could actually calculate the wave function of a person. And here's where it's possible, but each particle of you has its own wave function, and to get the whole wave function you have to combine them all, so you have to know all of those, and it's even more daunting than the throw of the dice, right? Remember we talked about if I throw a dice at the microphone, theoretically we could measure all of the parameters and predict the outcome of the dice, but realistically that's overwhelming amount of information. We just can't measure that much. Same problem with our own wave function. Theoretically, we could calculate it. We calculate the wave function of a baseball, for instance. You could potentially, if you could measure the entire wave function, predict exactly where the baseball was going to hit the catcher's mitt, or exactly where it was going to go once it left the bat. Those kinds of things. But those are just overwhelming amounts of measurements that have to be made to get that much information. And we're going to be talking a lot in lab about how the universe really might just boil down to that level. And that is what we mean by the universe is really just information. It's information about the quantum states of particles, of quantum particles. And that's really where everything goes. Now, we've gone through this. Quantum particles can occupy only discrete energy levels and not be anywhere in between. They can tunnel through barriers. They can appear and disappear just spontaneously. That's part of what they are doing in tunneling and so forth. again, this is all very seemingly somewhat impossible, but they actually do this. We measure them, we take advantage of these things. And the last one, they can become entangled. And this is one of the more interesting ones, actually. When two quantum particles interact, particularly electrons, they take opposite states in many ways. And they maintain that relationship no matter how far apart they are separated. So you could take two electrons, you could entangle them, you could keep one here on Earth, you could take another one to the moon or wherever. If you change one, you instantaneously change the other. Now again, that's what Einstein called spooky action at a distance. It's instantaneous. You change the state of one, you instantaneously change the state of the other, no matter how far apart they are. Again, there's no way that information can travel from one to the other in any understandable way. It just does. I got to pause for effect here. Let that sink in for a second. Now, one of the possibilities, though, and again, we'll come back to this possibility perhaps in lab again, is what if we could entangle particles and take the partners, like say we have a base on the moon. Right now, if we wanted to, if we had people on Mars, it takes, what, about a day for a light to get from the Earth to Mars? So any signal that we send right now is delayed. We have to send the signal, we have to wait. It's like 2 days later, we actually get an answer. Well, if we could take a quantum communicator, we could communicate instantaneously. It wouldn't require any time in between, because whatever you do here is instantaneously having its impact over there. Problem is, you can't string these things together. You can only do it one pair at a time. The second pair interrupts the first pair, and then you're lost. Okay? So you can't make a message out of it. At least not yet. They're working on it. All right, let's go to the last, really most bizarre interpretation of quantum reality, because it's sort of where we hear a lot of things going on today, and it's getting more and more serious consideration from physicists who are looking at it. Initially, this was sort of like plate tectonic or continental drift when Hugh Everett first suggested this. He really was ridiculed. Matter of fact, it sort of ruined his career. In retrospect, now he's getting a little bit more respect from physicists, though it's begrudging, but they are having to at least acknowledge the possibility of what he suggested. And his suggestion was basically, well, if you look at Bohr's interpretation, it's called the Copenhagen interpretation of reality, it's really not satisfying to simply say that we're experiencing a reality that just randomly happened because of all of the various interactions of quantum states in the past, that they become determined over time. But what he suggested was that every quantum determination basically has to exist in its own world, and that every event then spins off a new world. The many worlds interpretation. You see the little, like the film strip down here, and this is basically Schrodinger's cat. It's alive in one universe, it's dead in another. Right? Whichever measurement we make just is determined by which universe we're in, not by the actual measurement. Now this solves a lot of problems in quantum mechanics, but it also presents a lot of problems sort of philosophically. It suggests, for instance, that everything that could have happened did happen in its own universe, and everything that can happen will happen in a different universe. And we're just sort of moving through this already determined existence. What direction, where we end up going, depends on the decisions that we make every day. So we're sharing reality up to wherever we may make diverging decisions, and then we go off on our own, in a way. It's kind of hard to get your mind around, but it's actually mathematically quite possible, and actually satisfies quite a few of the challenges that quantum mechanics poses to us. But on the surface, everyone said, that's just silly, right? That's just silly. And they initially would say, even if it were true, we could never know, so it's just a silly argument anyway, because how would you ever be able to measure one or the other? And of course in the movies they do this all the time. That's why Spock goes from one timeline to another, and we have two Spocks in the latest Star Trek movies, right? Because he just sort of flipped. Here's his timeline. Oops, he got sent back to this point in another timeline, but now he's in that timeline. It's an easy solution for science fiction, but it's also starting to grow on physicists who are looking at possibly being able to make measurements that could confirm this. And so we'll talk more about that when we get to string theory, which is where we might be able to actually make some of those measurements. Yes?
Does this relate, we were talking a few minutes back about how Aristotle's idea of, future causes and
Right.
whatever is wrong. Does this relate to that
Well,
in some way, or?
Not in, okay, in a sense it seems to, but not really. Because again, in any given timeline, in any given universe, there are no future causes. Our future does not act on us. If something, and this is the other thing about the time paradox, time travel type paradoxes, and the idea that if you went back in time and killed your grandfather, what would that do to you? Well, the solution is you wouldn't be killing your grandfather. You'd be killing your grandfather in some other timeline. So you just wouldn't exist in that timeline. That's already happened. So it's not really a future cause in the sense that Aristotle was describing it. Nothing in our future will act on our present or our past. If you were able to do that, it would just spin off a new timeline, which create a completely different universe. Wouldn't be our universe. So again, there are a number of science fiction movies that have tried to explore that a little bit, or tried to use that as a device to present different realities. It's always been sort of fun in science fiction to say, what if, Hitler had won? What would the world be like today if Hitler had won World War II? Or what if, I'm trying to think of the different Star Trek episodes. What if Rome had never fallen? What if the South had won the war? The Confederacy had won the Civil War. I mean, there's all kinds of things like that you can, in literature or movies or whatever, sort of think about. And this is the device that gets you there in science fiction, that where you might be able to suspend disbelief enough to believe you're in a universe where that was actually the reality. All right, I'm going to talk the last couple slides about the actual technology that is produced using quantum characteristics. The most fundamental is the transistor. It was the first quantum technology. There's this amazing story of quantum mechanics is the same author who wrote the the physics of superheroes. It's about as good an explanation of everything that I'm trying to explain to you as you can get, with just a minimal amount of mathematics. It's really not very complicated at all. It takes a little bit of mathematics to explain this better than what I'm trying to do. So I would recommend that if you're interested. That's a good source to go to, and he has fun with it, just like he did with the physics of superheroes. He does a good job of explaining things. So if you want to know how does a transistor work, because believe me, if you go to how stuff works, or WikiHow, or any of those sort places that try to explain this stuff, it's hard to follow exactly how a transistor works. It's a sandwich of basically of switches that if you hit it with a piece of energy can either become a 1 or a 0, and then you put those together into circuits and make an integrated circuit, and that integrated circuit can do a calculation, and we've gotten to the point where you can put so many bits on the integrated circuit. A microchip, for instance, in your computer has millions or billions of these operating at one time, so you can do a really complicated calculation very quickly. But it's still just that 1 or 0 series of decisions basically integrated onto a circuit, these transistors one at a time. Again, they can be very small. I mean, we're really talking about a quantum level here. We're talking about electrons moving from one place to another, either in the 1 position or the 0 position, and we can move them back and forth with electrical signals and use that as a language. So a better explanation of that is in that book. Lasers are in fact quantum mechanics because you're taking photons and controlling their behavior in a very constrained way, and it requires quantum manipulations on the quantum level to do that. One of the more interesting recent ones that's becoming more and more popular are the LEDs, light-emitting diodes. LED TVs, LED screens, these are sort of the height of technology right now because you really are getting every little flash of light is the release of a photon from one of these light-emitting diodes. So you're able to, again, you could put a series of diodes together and do the same thing that transistors do. We could, if we had LEDs and light bulbs and all of these lights, essentially turn the lights into the mainframe for the campus. We could send, that could be where all the wireless signals are coming from. There's a TED.com video showing this, that simply by flashing those lights faster than the eye can see, you would just see a steady stream of light, but that would be sending the signals that a wireless signal is sending. So we could just, that'd make our Wi-Fi a little bit more effective because you could have Wi-Fi in every room, right? Just in the bank of lights in that room. So there's amazing things that are going to happen with LED technologies. It seems really simple. When you have an LED flashlight or something, and wow, look how bright that is for such a small little bulb. Because you've got trillions of photons being generated by these LEDs, and they're renewable. The only reason they don't last forever is because of the construction of them. But the principle of the quantum particle, the emission of light, basically as soon as you turn it off, it just restores from the various photons in the environment. So it never runs out of energy to create light. It just breaks down over time because of the materials it's constructed from and the heating of it as we control that emissions. But LEDs are amazing. Atomic clocks, essentially that's a quantum level technology. It's our ability to measure time now in such perfection that it's pretty amazing stuff. All right. In the future, and again, we'll develop this more in lab. I am out of time, aren't I? I've mentioned all three of these already, but I want to, one thing, the reason I have a puppy in the box, the cat and the computer, Schrodinger's cat, it's how the computer works, I've already told you that, but the problem is, for quantum computing or quantum communication, you have to be able to make the measurement of the quantum particle without actually measuring it. How do you do that? How can you possibly know what the quantum particle state might be without actually measuring it and determining what it will be? And the method is called quantum interrogation, and the example is a puppy in a box instead of a cat in a box. You want to know if the puppy is awake or asleep. So how do you do that without opening the box? Because if it's asleep, you don't want to wake it up. Poor puppy. If it's awake, you don't want it jumping around and jump out of the box, so you want to know whether it's awake or asleep without opening the box. So you slide a steak in there. And of course, if the puppy is awake, it'll eat the steak. Of course, a steak will probably wake the puppy up too. It smells really good. The puppy will wake up and eat the steak. But if you slip a salad in there, well, the puppy's not going to eat the salad if it's asleep. The salad's not going to wake the puppy up. It might nibble on it or mess it up if it's awake. So you put the salad and the steak in superposition and you slide that in there. If you do that once, you get a 50-50 estimate of whether the puppy is awake or asleep. If you turn it, a turn in superposition, do it again, you now have a 75% probability of knowing what the puppy is. If you do it again, it becomes, and you can see how you can approach 100% by repeatedly making those measurements of steak, salad, superposition states. Now, if you translate that to the quantum level, you could test or interrogate the state of a quantum particle in those repeated measurements to the point where you would know for sure, like 99.999999% certainty what the state would be, and then use that as the basis for a calculation. You do that repeatedly, you have the same kind of possibility as an integrated circuit to make those decisions. But you can do it about 10 to the 16 power faster and more number of calculations. It really is an astounding possibility, and we'll talk about some of the ramifications in lab this week. All right, let me get to the quiz. I'm going to have to go in and fix this. This little pop quiz at the beginning doesn't look right. So I promise I will try to fix that. Well, it won't, not in time for you guys, right? Next semester. All right, quantum mechanics quiz. According to Einstein, ghosts only exist at a distance. Okay, that's neither true or false. You're going to see quickly in these 5, it doesn't matter what you say, everything's right. This is just sort of a joke. Einstein described entanglement as spooky action at a distance. He said that's impossible. Nothing can travel faster than light. You can't possibly have information traveling from one quantum particle to another across any distance with nothing going on in between. So whichever one you want to say. False. I mean, that isn't what he said. I guess false would be the better answer there. He did not say that. According to Schrodinger, you should own a dog instead of a cat. I don't think Schrodinger really cared, but Schrodinger's cat is often thought of as, sort of this odd cat, this both alive and dead at the same time. And the little puppy in the quantum interrogation example gets to eat steak, so it's a lot better off. Okay, in a different reality, I'm a duck. Does anybody remember Howard the Duck? There was a comic book called Howard the Duck. They even made a really bad movie out of it. I think Robin Williams was the duck. I can't remember. But it was a really funny comic book. The movie didn't do it justice. But yeah, it was about a duck in a different reality who somehow got stuck on Earth. And he's just as, as intelligent as anybody else, but he's a duck. So Howard the Duck. So in a different reality, I'm a duck. Maybe? I'm going to say true? Now, according to Heisenberg, wherever you go, there you are. I saw a mug one time that said that, wherever you go, there you are. Sort of like an existential philosophy of life that, be in the present, but it sort of makes, I think, this measurement problem kind of funny. So what do you want to say, true or false? Wherever you go, true, right? I mean, kind of true. Now, if you were a quantum particle, you could be in more than one place at once, but as a human being, we're stuck wherever we go. That's where we are. And number 5, beam me up, Scotty. Now, the way the transporter works in Star Trek would require you to actually be turned into your quantum state, physically take you apart and put you into that superposition state, every particle of your body, and then send that somewhere and reconstruct it. That really is, impossible is not the right word, but not really wise. But what we might be able to do is take the information and send the information wherever we want it and make a copy of you. So I'm going to say false. Now again, I have no idea how I coded this. Let's see. But don't worry, everything is correct. I think I set it up that way. Whatever you said is correct. See that? Everything, well, except for this one. That one does have to be false. But everything else can be either true or false. All right, anyway. See everyone in the lab who's coming today.